Welcome to this PowerPoint on electric field. Today we're going to be talking about the concept of electric field and seeing how it relates to electric force. To understand electric field, we really should understand the idea of a field in general. We define a field as a property of space which results in some sort of force. So we have a gravitational field above the Earth because we have a gravitational force that exists at all points. The force only exists when a mass is there, and because the mass exists and experiences a force, there is a field. If we don't have a force, we don't have a field, and if we don't have a field, we don't have a force. And the direction of the field is determined by the direction of the force. Now, if we consider 2 points above the Earth's surface, point A and point B there, and we might be able to find the strength of the field by taking the amount of the force and dividing it by the size of the mass. So little g, the acceleration due to gravity, is what we call the gravitational field. Every point above the Earth's surface we can find the force F if we know what the gravitational field is. So because we know that g is equal to 9.8 on the surface, slightly less than that above, our force is equal to mg, and so we can find our force. The force is real, but the field is just a way of describing what the space is doing, the changes to the space around our object. So our force is pointing in toward the center at A, and it's pointing in toward the center at B. And again, the magnitude and direction of the field is dependent on the weight here, which is the force F. The similar concept with electric field is if we had a positive point charge, big Q, and we were considering a point P that was distance r from point Q, if we put a positive charge at point P right here, it would feel a force F that would point up. Because that force F exists, we know that there must be an electric field there. So the electric field exists at point P if the charge has a force. The direction of the electric field is in the same direction as the force on a positive charge. That's really important. So our electric field is up at this location. And the size of that electric field is given by the formula. Electric field is force per charge, force divided by charge, where force is in newtons and charge is in coulombs. The field is a property of the space, so around a specific object, the field is the same regardless of what is there. What is different is the direction of the force. So if we put a positive charge at point P, the electric field points up and the electric force points up. But if we put a negative charge there, the electric field points up and the electric force points down. The field will exist whether or not there is a point or a charge at that point, and the direction of the field is always away from a positive Q charge. For a negative Q charge, for a source charge of negative Q, the electric field will always point down because the force on a positive charge is with the field direction, so it goes down. Again, the force on a negative charge will go opposite the field, so it will go up. So the electric field in the vicinity of a negative charge is toward the charge, in the direction that a positive test charge would move. The magnitude of the electric field is given by force per charge, so that's newtons over coulombs, and it's the force per charge that would be experienced by any charge placed at that location. So our important equation here is that the electric field intensity is force per charge, F over Q, and the units are newtons per coulomb. And again, the direction of that electric field is the same as the direction that a positive charge would move if it was placed at that point. There doesn't have to be a charge there, but if there is one there, the direction that that force would point is the direction of that field. So here's an example. A positive 2 nanocoulomb charge is placed at a distance r from a negative 8 microcoulomb charge. So this is our negative 8 microcoulomb charge. We place a positive 2 nanocoulomb charge here, and we want to say if the charge experiences a force of 4,000 newtons, what is the electric field intensity at that point? So go ahead and pause and take a look, and welcome back. So we would make sure that we are noting that the direction is down, right, because we have a negative Q here. And if we're placing a positive Q up here with it's experiencing 4,000 newtons, we know that our electric field must be 2 times 10 to the 12th newtons per coulomb downward. Now notice we didn't use at all this -8 microcoulomb charge. We took our 4,000 newtons of force and we divided it by our charge that was up here. We didn't use this one at all. We'll use it later, but not right now. This would be the same regardless of whether or not we had a +2 nanocoulomb charge here. If we had a smaller charge, we would have a smaller force, but we'd have the same electric field. It's a property of that specific space. Here's a second example. In between two parallel plates, we have a constant electric field. We'll talk about why that is sometime soon. But if we have a constant electric field of 40,000 newtons per coulomb, what are the magnitude and direction of the force on an electron that passes horizontally between the plates as shown like this? So if the electric field is in between these plates, what's the direction and magnitude of the force on this electron right here? Go ahead, pause and take a look. And welcome back. So remember, our electric field is downward because it's going to point away from positives and toward negatives. So our electric field is force per charge, so our force is charge times electric field. So if we know that our charge is the charge of an electron, 1.6 times 10 to the -19th coulombs, and 4 times 10 to the 4th is our electric field, we know that our force is 6.4 times 10 to the -15th newtons upwards. Now keep in mind, we could have used a negative sign here, and the negative sign would have just told us that the electric force pointed in the opposite direction of our electric field. In this case, our electric field goes down, so our electric force goes up. We can use this concept of electric field as force per charge to determine the electric field at a distance from some single point charge, Q. So if we have this pink point charge, Q, here, and I wanted to know what's the strength of the electric field at point P if I know what R is, we know that we have a force going out, so our electric field must go out as well. And our electric force is given by Coulomb's law. F equals K times Q1 divided by Q2, K Q1 Q2 divided by R squared. So Q1 is this one, Q2 is this one, however you want to do it. We have this charge and this charge. So K, big Q, little q over R squared. The electric field then is force per charge, which is KQQ over R squared divided by little q, right, the little q up here. So we're left with the fact that the electric field around any single charge Q is K times the charge of that object divided by the distance that you are away from it squared. So here's an example. What's the electric field intensity at point P, a distance of 3 meters from a negative charge of 8 nanocoulombs? Go ahead and pause and take a look at that. And welcome back. So first we have to find the magnitude of the electric field by doing KQ over R squared. So we have K is 9 times 10 to the 9th. Q in this case is 8 times 10 to the -9th. It's nanocoulombs, and we're dividing it by 3 meters squared. So our result is 8 newtons per coulomb. 8 newtons per coulomb. The direction, remember, is the direction that a positive charge would feel there. So if we put a positive charge there, it would attract toward the negative Q. So we have our electric field toward Q. We can also take into account multiple electric fields by simply vector summing the electric field. So if we have a point A that's being affected by Q1, Q2, and Q3, each of them has an electric field that points in some specific direction. So to find the overall electric field, we would just using vector addition, add the 3 of those together. So depending on the size of the charge, it could point in any direction. And again, our magnitudes are given by KQ over R squared. Now the final thing that we have to talk about here is how to draw the electric field. Electric field lines are what we use to determine or to describe the direction and the magnitude of the electric field around any point charge. So say we have some positive point charge Q. The electric field might look something like that. The electric field lines represent the direction of the electric field at any given point in space. So for a positive charge, it points out. For a negative charge, it points in. That will always be the case. Electric fields point out for positive charges and in for negative charges. So to draw field lines, we have to remember that the direction of the field line is the same as the motion of a positive charge at that point, and the spacing has to be such that they're close together where the field is strong and far apart where the field is weak. So if we look back here, the field lines are much closer together than they are out here. Same thing here. They're closer than they are out here where they're farther away. And so if we have a Q1 and a Q2, we know that the electric field from Q1 is going this way, and this way, and electric field from Q2 is going this way, and this way. So the result is that our electric field points something along those lines there. So we have some sample electric fields. If we have two equal but opposite charges, this is called a dipole. That's what the electric field looks like. If we have two identical charges, both positive in this case, they would point like this. You'd have a dead zone right in the middle here. The lines leave positive charges and enter negative charges. They always point away from positives and toward negatives. And the field is the strongest where the field lines are the most dense. So we know then that the electric field is densest when we have the most number of lines passing through some area here. In summary, we have two real equations here. We've got the electric field intensity, which is force per charge, which is kq over r squared, and the electric field near several charges is the vector sum of each of those values right there. That's it. Thank you.